Hey geometry students, in this lesson we are going to be talking about one of the ways of identifying triangles that are congruent to each other. We're going to be talking about side-side-side congruence. In this lesson we're going to be doing one of the most important things we'll be doing in algebra in upcoming lessons. We're going to be identifying ways that we can identify polygons that are congruent to one another. And we're going to start by focusing in on triangles. We're actually going to find out that there's a lot of different postulates related to triangles by which we state that we can assume triangles are congruent. And we're going to be using these postulates in proofs. So what we're going to be learning in this lesson is very, very important for moving forward. And just know you're going to build a collection of tools to identify congruent triangles. Let's get started, but we're going to be talking in general about polygons for a little bit. First of all, we need to define what corresponding sides and corresponding angles are in polygons. So a corresponding side are sides that are in the same position in two different polygons with the same number of sides. Now I'm going to say that in order for sides to be corresponding, the polygons don't necessarily have to be congruent, although usually they are when we talk about corresponding sides, because that's what makes sense. But at the very least, the polygons have to have a very similar shape, if not the same essential shape, for us to be able to figure out what corresponding sides are. Now, you could do corresponding sides in two polygons that aren't the same shape, but first of all, why bother? There's really no use for it. And secondly, it's really hard. Like if we have a convex and a concave polygon, it'd be kind of difficult to match up the sides in any meaningful way. Now you could count, like this is the first side, now we're going to count 3 sides from this first side. That'll be a set of corresponding sides. But again, it really doesn't matter unless the polygons are at least very close to each other in shape. Okay, angles can be corresponding too. So angles that are in the same position in two different polygons would be corresponding angles as long as the two polygons have the same number of sides. Now we're going to see in this lesson about congruence that corresponding sides and angles are really important, and they're going to refer to sides and angles that are exactly the same because they're going to be congruent in this lesson. Are they always congruent? No, but they are going to be congruent in this lesson. Now, what is a congruent? I've been talking about congruent a lot. What is a congruent triangle? In congruent triangles, all of the corresponding sides and angles are congruent. Remember, corresponding sides are in the same position, so the angles and sides that are in the same position as each other are congruent. And then lastly, I'm just going to make this statement because it's kind of hard. It's kind of hard to, when we're naming some polygons, especially triangles, we only have a couple of angles for reference, to identify which angles match up to which other angles in the other triangle as corresponding. But it's really important that you take the time to think this through and to do this correctly. When naming congruent polygons, you need to name them so that the congruent points and vertices are in the same order. So if I say triangle ABC is congruent to triangle DEF, that means that angle A and angle D are congruent because those are the first ones I mentioned. B and E are congruent because those are both the second ones I mentioned in each triangle. Okay, we're going to be looking at an example of that in just a little bit. Now on to postulate 13, the side-side-side congruence postulate. If 3 sides of one triangle are congruent to 3 sides of another triangle, and keep in mind triangles only have 3 sides, so all of the sides are congruent, then the triangles are congruent. Please keep that in mind. So what is the side-side-side congruence postulate? Well, it states the only thing we need to know about two triangles for them to be congruent is that the sides are all congruent. That makes the triangles congruent. One other quick note. There's something called triangle rigidity. If all sides of a triangle are a fixed length, there can only be one possible size and shape that describes the triangle at the fixed lengths that we've defined. That is not true for other shapes. I want you to think about like a square or rectangle or a parallelogram, really any parallelogram for a moment. If I gave you all of the side lengths in a parallelogram, you could still change the shape of the parallelogram by just tilting the parallelogram more, bringing the top line closer to the bottom line as you tilt the parallelogram sideways. You could change the shape of the parallelogram while maintaining the side lengths. You can't do that with a triangle. We're going to be looking at an example of that in just a second. And then just one little hint for remembering how this works out, and you can use this in proofs as well. CPCTC stands for corresponding parts of congruent triangles are congruent. So the corresponding angles are congruent, corresponding sides are congruent. All right, now let's take a look at what this means here. Here I have a triangle. Notice that this is a scalene triangle. All three side lengths are different. And I know nothing about the angles here, but I know that all three angles are going to be different. They have to be because all three side lengths are different. Now what I'm going to do is I'm just going to make a copy of each side of this triangle, and I'm going to embark on a task, okay? I wonder, can I rearrange these sides so that they all connect to make a triangle, and they're a different shape than this triangle up above? Okay, well, so my first instinct is, what if I move this line over here? But I got to keep in mind, I can no longer use this line to connect them to make a triangle, so that's no good. Okay, so what if I take this line and move it up here? Aha, maybe I figured something out. So move this one up here, and then I'm going to move this one over here. And let's see if I can get these to connect correctly. I just need to adjust, and let's see. Do I have congruent triangles? Well, let's just take a look at what I could do with this one. Okay, so I'm going to group this one all together, and then I'm going to rotate it. There we go. And let's see if we could just drag it. Notice that it's still, like I can rotate it. It lines up perfectly with the original. Yes. Even if I try to make it not congruent to the first one by dragging the sides around, there's nothing I can do to break the congruence. It's always going to be congruent to the original triangle. Okay, let's get it back to where it was. And then what I'm going to do is I'm just going to move this over a bit, and let's label all of our points. So I'm going to label our first triangle A, B, we'll put B there, and C, okay? Now, I have to pay attention when I'm naming the second triangle. A has to be the angle between the side that has 1 tick mark and the side that has 3 tick marks. I notice it's one of the acute angles in this obtuse triangle. It's going to be this angle over here. So I have to, if I'm going to say ABC is corresponding or is congruent to DEF, then A and D have to be the corresponding angles that are related to each other. E is going to be the top angle down here, okay? And then F is going to be the remaining angle, the one that is combining right where 2 and 3 come together. There we go. All right, now let's look at what CPCTC tells us. When two triangles are congruent, the corresponding parts are congruent. So if I have triangle ABC congruent to triangle DEF, then by CPCTC, all of the following statements can be written. A is congruent to D. Remember, those are the one, between the 1 and the 3 tick mark sides. That's that same side, so that must be the congruent angle. B is congruent to E. C is congruent to F. Segment AB must be congruent to segment DE. Well, the tick mark there really helps because I know that they're marked congruent. BC to EF, and then AC to DF. There we go. Now, just one more thing before we leave this topic and move on to the next thing that we're going to be doing, which is our practice problems. What if I took a triangle like this? We're just going to move it, we'll put it down here. And what if I made a copy of the same triangle, I'm just going to group this together again. And then I'm going to do something. We're going to go to Format, Reflection, and that's not what I want to do. Size and Rotation, and then I am going to flip this vertically. Boop. There we go. Hey, do I still have congruent triangles? Now, watch what I can't do anymore. Ugh, I gave it reflection. I thought, because it's called reflection when you, okay, we're going to turn off reflection. There we go. Is it possible for me to rotate this so it perfectly lines up anymore with the original one? You'll see that there's actually, now that I've flipped it, there's no way that I can rotate it to coincide with this previous triangle. And that's going to be kind of a problem, right? Isn't that going to make it not congruent? Well, okay, let's just go back to our definition of congruence by side, side, side. If three sides of one triangle are congruent to three sides of another triangle, then the triangles are congruent. Nowhere does it say that you need to be able to rotate them so that one perfectly overlaps the other. The triangles are congruent simply if their sides are the same. So these are congruent triangles, even though one is a mirror image flip of the other. And that's going to be important for you to realize. You can have congruent figures that cannot be made to coincide, but they're congruent because the sides and angles are congruent. Okay, so I've basically laid those right on top of each other, next to each other, and you can see that these are congruent triangles. They just can't be made to rotate into one another, but it does have side, side, side congruence, and therefore the triangles must be congruent.